Presentation. Perfect. So, hi everyone, my name is Caroline, and I am the Confidential Computing OS Platform PM at Microsoft. And today I wanted to talk about a very, very exciting project that we've been working on for a very long time, and it's called OpenHCL. And this is our new open source paravisor for confidential VMs. And I sometimes will say CVMs just because I'm very used to saying that. So if I say CVMs, I just mean confidential VMs. I think before we dive into specifics of OpenHCL, I wanted to ask here if people are familiar with the term paravisor, because I feel like when I look online, there's not too much information around what this is. And I don't think of it as a Microsoft term. I think of it as a generic term. It just so happens that I think Microsoft is the only company that's implemented one. Again, if anyone knows differently, please let me know. But yeah, does anyone know one or want to kind of put something out there?
It's not a Microsoft only term, although the Zen hypervisor project would say, I think that theirs is a paravisor, but you might disagree depending on your definition. So I think it's probably worth having.
Oh, that's great input. I mean, I can tell you what how I think about a paravisor, and I would love to hear your thoughts on if that meets their definition, and would love to hear more about them too.
Well, they're part of Citrix, or they were been around for 10, 15 years. So
yes, I mean like their paravisor implementation.
Yeah, sure. I can't remember the details. Anyway, carry
on. Well, basically, a paravisor implements the TEE enlightenments on behalf of the guest OS, so that the guest OS does not need to be fully inlined. It can run mostly on modified, or in theory, even completely unmodified. So this paravisor enables guest operating systems that are not fully inlined to run inside a CVM. And not fully inlined guests today basically includes legacy and future versions of Windows and legacy versions of Linux. And by legacy, I just mean like old versions of Linux that don't have the alignments. I don't know the specific like kernel versions, but I could put those in the chat later. A paravisor, by definition, must run at a higher privilege level. And this privilege separation is enforced by the confidential computing hardware platform itself. So on TDX, that's TD partitioning, and on SVSMP, it's the VMPLs. So I'll pause here. What do folks think?
When you say enlightenments, you're speaking specifically about instructions that a guest OS would expect the machine to support, like TDX hardware or SVSMP hardware, but that the hypervisor doesn't support. And so the paravisor has to intervene to do work so that the guest OS doesn't have to trust the hypervisor to do those confidential things. Is that a rough definition?
Exactly. Basically, traditional guest operating systems are used to interacting with the virtualization stack in a specific way where they like inherently trust it. And so in a confidential computing platform, that no longer is valid. So they need some alignment, some changes, some hardening, etc., to interact and basically like defend itself from things that are outside the TCP.
So paravisor supports paravirtualization.
Sorry, I didn't understand the question.
So we have paravirtualization. Paravisor is the one which supports this paravirtualization.
Yes. Or sorry, Dan, you went off mute. Were you gonna?
Do you know paravirtualization?
Yes, but I think, sorry, I still don't understand the question.
So
I think what he's saying is that a paravisor supports paravirtualization.
Yes, exactly. Yes, and I think hopefully that can also become a little bit more clear once I show a diagram, but yes, certainly. In fact, we have like paravirtualized devices in running inside of the OpenHCL paravisor.
So there is this something called ultravisor, which is in on the IBM Z S390s, which does something similar. Earlier, you were asking whether you've heard of paravisor, right? There is something like there is something called ultravisor in the IBM land, on the IBM Z land. Ultravisor, which
Okay,
which
awesome.
does something similar like what your paravisor is doing.
Thank you. That's great to know. Like I said, it was just to my knowledge of what I had seen was out there, but I'm glad to know there's other things like this.
Yeah,
Or
that's
maybe
been
that are really this.
yeah, that's implemented on S390s, and also it was used on OpenPower.
Just one question I have on this topic. So you're saying that enables unchanged practically OS to run inside the guest. So what are the changes that we typically need to do? Because why is not this possible today? I think Linux, you can run it in practically unchanged. You need guest drivers or something, a couple of drivers that you need for the attestation, but there are no changes to kernel or even rootfs or something like this.
Yes, so I'll go into a little bit of that detail in, I think, to hopefully answer that in the next few slides, so that's okay. So before I talk about OpenHCL, I'll talk about our first implementation of a paravisor that we had in Microsoft. And so basically what this diagram is meant to show is that for traditional VMs, we would usually have emulated devices and UEFI services running in the host. But when we implement the paravisor, we actually moved those emulated devices from the host to the guest paravisor. And this enabled confidential VMs to have a TPM device as well as secure boot. So you can see it's these two things here. Again, the fact that we have this privilege separation between the guest paravisor and the guest OS, and it's protected from the host, is exactly kind of what allows this model to work. Something else is we began storing guest state in this new special file that we call the VMGS, the VM guest state file. And the VM can now store its secrets here, and they're inaccessible to the host in the case of a confidential VM because they're encrypted. So the host only ever interacts with an encrypted VHD. And the guest paravisor basically takes care of doing that on behalf of the guest. So the guest still will interact with UEFI services the way that it traditionally did. And the difference is it won't be emulated by the host. It'll run in the guest paravisor and it'll interact with this file. I think one of the questions was like, what other changes are required besides the drivers? I think to truly defend against like potential interrupt-based attacks, traditionally the APIC emulation is done by the hypervisor, but with a paravisor, that can help in actually doing some proxying for the interrupts. So when an interrupt is coming from the hypervisor to the guest VM, the guest paravisor can validate that before re-injecting it into the guest OS. And then the other kind of enlightenment is there are new exception types that a guest needs to be aware of when running on a confidential platform. These are actually hardware platform specific. So they have like different terms on like AMD and Intel, et cetera. So you need to be in line to know how to handle that special exception type. And if you have a guest paravisor, it can just take care of that on behalf of the guest. So the guest doesn't need to have those changes. Lastly, there's also remote attestation. Since that is kind of by definition part of what a confidential VM is, the guest would also need to do that. If it's a confidential VM, it would need to perform attestation. Whereas if you have a paravisor, that can also do that on behalf of the guest. The guest can still do it afterwards. There's no one or the other, but if the scenario requires it, the guest paravisor can do this. Hopefully that answers part of the question that was raised earlier.
I'm guessing so. Feel free to move along.
So
Okay.
maybe I just have a question here for the VTPM. Does it implement a virtualization of TPM here as well, or?
Yes. So it is a VTPM. I think there it's listed as TPM, but it's technically a VTPM implementation.
So it implements it. So in somehow it is similar also to Coconut project from SUSE, which does the implementation of VTPM through SVSMs.
Yes, and I actually have a slide on Coconut too.
Very interesting. Yes, thanks a lot. Yeah, great.
Yeah,
And also I'm reading that there are interactions with acceleration, accelerated IOs, so interaction with GPUs, etc. Is it implemented through the paravisor also, or maybe I'm running ahead?
No worries. I didn't understand the question. Like, for the confidential GPU products we have in Azure, you're asking what the role of the paravisor is?
No, actually, I read in the on the blog post of the Microsoft here that it also implements a paravirtualized I/O model.
Yes. I'll get to that.
Okay,
So this
I'm
is
running.
this
Okay,
is the old
thanks.
paravisor. The new OpenHCL paravisor has that new functionality, which is really cool.
Okay, great.
So
Thanks.
OpenHCL is basically the next generation paravisor, which is, I'd like to clarify, it's going to be open source very, very, very soon. It's not today, but I'll be very excited to share the repo and all that with everyone here once it is. Again, very, very soon. I just can't say a specific date. But in addition to what the old paravisor had, it has more diagnostic capabilities. And sorry, that both is a typo there, but that helps debug CVMs, which is like really, really useful because debugging CVMs in general is a hard area. So this is something that, because it's inside the TCP of the CVM, it can basically, again, just protect. So any information that is going to go out to just externally for debugging purposes, the paravisor can in theory protect it in whatever way it needs to, whether that's encryption or something else. Device emulation is something we had before, but now we have a larger set of emulated devices. And these are exposed via standard device interfaces. And then I think what you were asking about in the blog post is device translation support. So basically what we have is we are able to assign, for example, an NVMe device directly to the VM, and it's assigned to the paravisor, and then the paravisor exposes this to the guest OS as paravirtualized SCSI, so as a paravirtualized storage device, as opposed to like a directly assigned device. And that really has allowed us to meet really great, I would say, targets for our storage and our networking capacities on like the very, very new Azure SKUs. And lastly, this supports virtual trust levels, which is a Hyper-V term for like privilege separation, both on x86-64 and on ARM. It also supports AMD SVSMP and TDX. And as far as the guest, it supports legacy BIOS, the Hyper-V virtual firmware, and also Linux Direct Boot. These are statements, again, about what the code itself supports, not about what is necessarily running in production today in Azure, but this is what the code is capable of today. So if we look at just really quickly the old diagram we had shown, we had the UEFI services and the emulated devices. And let's say these things are the core paravisor support. So in this new OpenHCL, these three are kind of like one box right here, the paravisor support. And again, we have like more emulated devices. And we actually moved the virtual devices to be inside the OpenHCL. So these are actually like the paravirtualized devices. So if we go to like the very beginning, like how traditionally things were done, these were running in the host, both emulated and paravirtualized. With the first round of paravisor, we moved emulated devices, and then we went all the way with OpenHCL and also moved a set of paravirtualized devices. As far as the components of OpenHCL, the two main ones are basically a VMM that is running mostly in user mode and implements a bunch of processes, and that runs on top of a very, very small customized Linux kernel that we basically built to, again, just be very light and have only the things that were needed to support the VMM running on top of it. And one key thing to mention is that the VMM itself is written in Rust as part of just our effort to have memory safety as much as we could. Any questions here? If not, a few other things about OpenHCL. Certainly, we're tracking the upstream kernel, and we really aim to upstream all the kernel patches or have a path to eventually do so. Again, these are the patches that are in that OpenHCL Linux kernel. We try to do as much as possible in user mode. Like I said, the VMM itself is in user mode. We have some device drivers in kernel mode, but the majority of them are in user mode. Not only do we use Rust, we try to use safe idiomatic Rust as much as we can. We also use async Rust as much as we can for performance reasons. And we try to keep the VMM code OS agnostic. So the VMM, like I said, runs on top of a Linux kernel, but we try to always keep that OS agnostic, so the VMM could run in other environments, not just Linux. And the OpenHCL is Linux today, but that way that VMM can be used for other scenarios in the future. And I think this is actually my last slide. How is OpenHCL different than COCONUT-SVSM? Well, it is just completely different in that it solves a different problem. So it's not at all something that is a competition or like a competing product, because Coconut is an SVSM, whereas the OpenHCL is a paravisor, and an SVSM aims to provide services to confidential VMs that are fully enlightened, whereas the paravisor aims to provide services. And maybe one service in common that was pointed out is like the VTPM, certainly, but to guests that are not fully enlightened. So the way things work today, if you're one or the other, you can only get this functionality from either an SVSM or a paravisor. And there is some shared functionality, but it's targeting like different types of guests. And that was my last slide. So questions, thoughts, any feedback would be appreciated too.
Great. Yeah, I know I was holding back. I didn't know how many slides you had. This last slide, though, does beg a couple questions for me. One, I think somebody asserted to me over the last few days that one of the things that you would do with OpenHCL is potentially run it within Coconut. So Coconut would be sort of a housing for OpenHCL. Is that a correct interpretation or possibility?
I wouldn't say we have a specific way in which they're going to intersect. I would say we are very, very much interested in them intersecting. Sorry. Yeah, and we've been collaborating with them and actually contributing to Coconut, or like some folks in Microsoft as well, because we think it's so valuable, and we definitely want to see an interception point in the future. We just don't know exactly when in the future and what it would look like.
Mm-hmm. Like Mike is next.
Yeah, so great to see this excellent work from our friends and colleagues at Microsoft. Thank you very much. So I think the thing that I like about this is the awareness that not everything is going to be enlightened, and I think there's a variety of ways in which things may not be enlightened. And when we start talking about lift and shift, is this a useful way to think about that? Because even if things are using more recent kernels, it may be that they don't know what to do with attestation, for instance. And so I think there's a really interesting set of useful discussions to have there. So I'm really, really keen. I would remind you that the CCC is always happy to accept interesting and useful confidential computing related open source projects. Whether this is appropriate for that, I don't know, but it's great to see it. Really like it, and please come back and tell us more about it on another occasion. Really, really liked it. Thank you.
Thank you so much. I really appreciate that. And yes, we're definitely very interested in the CCC support. So we can talk about that another time. But for today, I just wanted to tell you about what this is. And hopefully when we talk about the latter, will already be open source. So, and to your point on lift and shift, that is exactly why we started this investment like almost a decade ago, because, we saw the value of confidential computing, and we really wanted to enable lift and shift of as big of an array of operating systems as possible, and customers using like a very old OS that might not have enlightenments, but certainly wants the security benefits of confidential VMs can hopefully benefit from this. And one thing I would like to say actually is the fact that let me go here. The fact that in this diagram, oh no, sorry. Do I not have one? Yeah, okay, so ignore the old paravisor. Focusing on the OpenHCL paravisor, the fact that this runs on Microsoft Hypervisor and Azure Host OS is very much a point-in-time statement. The way we've designed OpenHCL is actually meant to be OS agnostic. That's actually one of the principles we listed. And we would very much be interested in seeing this be adopted by other virtualization stacks, other hypervisors. It's just not something that is like fully supported today, but hopefully now that it's open source, we can contribute with other people who have really great expertise and make that happen in the future. But yeah, like just again, want to clarify, that's just a point in time statement. Like our whole goal and the way we've designed this is to be OS agnostic and platform agnostic.
And so a potential consequence of that could be that if your host operating system is Linux and and you want to run an unenlightened Windows guest, this could in the future maybe help fill that gap.
100%. That is the aspiration.
Very cool.
Neat.
Drasco, I see you look like you're next in the queue here.
Yes, thanks. So thanks for this great work. It looks extremely useful, and especially connected to what I was telling before, that we were particularly forced to run our solutions on bare metal machines. And one of the things that we struggled with a lot is virtual TPM. This is why my question was there. And Coconut has only recently added completely this support. However, this seems as a very interesting approach that is wider than what Coconut is addressing. I have a few questions. One is, I think you already maybe touched on this, but this hypervisor, so the availability of running it in QEMU, so this is what we are using as a hypervisor. Then the question about of applicability of this on confidential containers as well, in Kata containers. And I don't know, they probably have their own kernel, but I think maybe this can be beneficial as well. And then finally, if you can give a little bit more details on those privilege levels and compare OpenHCL with Coconut when it comes to those privilege levels in which they are run. So those are my three questions here.
Sure. I think the I'm trying to think what order to tackle them in. Maybe for the privilege level one, the last question you said. So I believe that Coconut also runs, and actually I'm gonna go here. I believe that Coconut also runs in VMPL0 on SCVSMP, but I'm actually not sure because there's 4 privilege levels, and as long as it's one higher than the guest, I think that's sufficient to keep the security promise of both an SVSM and a paravisor. So for our implementation, we did VMPL0. I can certainly follow up and find out if Coconut is also VMPL0, but I think if your question was, do Coconut and OpenHCL use the same privilege levels, like the same boundary
No.
between privilege levels, it's VMPL.
Yeah.
Or did I misunderstand your question?
Yes, this is what I wanted, because I was reading quickly the slide and just wanted to understand, especially we are using SCVSMP, so VMPL0 would be the place I would also put it in. So
yeah, because it's the highest.
Yeah.
And that leaves the other two open for possibilities in the future. For example, for Windows Guest in Azure, we actually do use one of those other VMPLs for Guest VSM, so to run the secure mode, if the guest wants that functionality. And VMPL4 is, of course, the guest OS, because that's the lowest privilege level. I'm sorry, I blanked on your other 2 questions.
About QEMU and COTA intersections.
Yes. Okay. Thank you, Dan. I think the answer for QEMU is absolutely the same as for anything. Like, without sounding like cliche, like the sky is the limit. Like, we really mean it to be OS agnostic and capable of running in different platforms. So I see no reason why QEMU would also be on the roadmap in the future. For containers, that is, I think, something we've talked about internally a little bit. But I don't think we've discussed it enough to really have a good answer for you. But hopefully it can also be useful for container use cases, like Kata containers. If you have any ideas, I'd love to discuss those too later. I just don't think we've explored it enough yet.
Sure. Thanks a lot. Thanks.
Yeah, thank you so much for the questions.
Okay, looks like Ram's up.
Yeah. Hey, hi, Carolyn. Thanks for the excellent presentation. So if I understand this right, your paravisor is running in the same address space as that of the guest. In other words, it's running in the same VM. Am I
Yes.
understanding this right? Okay. How does it get deployed? Does it get deployed from the hypervisor, or does it get deployed as part of the images that is running within the VM, maybe as part of the distro images? Like how exactly does the paravisor getting deployed in the VM?
Yes, that's a great question. So, at least in Azure's current implementation, again, this could change in Azure and it could be different for other implementations, but the host, when it launches the VM, the first thing it loads into the VM is actually the paravisor itself. So that is the first thing that loads in the VM. And the host basically has a file that has some instructions and some offsets that tells it how to set it up, if it's TDX, if it's SMP, etc. And once the paravisor loads, that then hands over control to the virtual firmware. So, for example, like the virtual UEFI, which then transfers control to the guest OS. So, as far as like the boot process, it looks very similar to a normal VM, with the exception of like now having the paravisor be the first thing that actually runs in the guest VM. And that gets loaded from the host today. So basically, the host just has a copy of that, of the OpenHCL, and it launches that.
right?
But
So
that could change in the future.
So it's essentially in a QMU kind of an environment, in a KVM,
Mm-hmm.
QMU, it's like deployed the same way as UFI is getting deployed in the guest,
Yes,
right? So
because
it's
I
one
think
of the,
they're both virtual firmware. Like you can view the paravisors as virtual firmware for the VM.
okay, sounds good. Thank you.
Yeah, thank you.
Okay, I've got two quick questions, maybe quick questions. I'm not sure. So you said that this will help a mostly unenlightened guest, and so I'm kind of curious what remains that must be enlightened for the guest to work, and then sort of a complementary question is, what wouldn't you get by using OpenHCL with an unenlightened guest that you would get with a fully enlightened guest?
I'll try to answer the first question, and then I
Okay.
think I didn't quite understand the second. But the first one is, we certainly didn't want to require the guest, if it's supposed to be, minimally enlightened, to have like significant changes and certainly not kernel changes. Those would actually be, I think, more extensive, especially in Windows with the memory manager to know how to deal with private versus shared memory. So we only modified the para-virtualized device drivers. So like the networking device driver, the storage device driver, it's the ones for Hyper-V. And this was done for both Linux and in Windows. And then we essentially backported that to like some older versions, which was, again, like less challenging because it was only drivers and it was a relatively small set of changes. But I mean, I could certainly provide, I think, maybe like the full list of changes and components that were altered, but it was very, very small. So that's why I say like minimally enlightened. In theory, the paravisor could actually do the bounce buffering on behalf of the guest in the future. So that alignment in the drivers is, of course, the bounce buffering and knowing how to deal with private versus shared memory. And so in theory, again, the paravisor could do that. That would have some performance penalty, which needs to be explored further to see if this is interesting to do. We've definitely done some POCs internally, but that's why I say like there's nothing stopping the paravisor from supporting any guest because it could technically do everything on behalf of the guest, including what those device drivers do. Can you repeat the second question, Dan?
You know what? I will defer that so that I can give Catherine some airtime here because Catherine hasn't had a chance to ask a question yet.
Thank you, Dan. Great talk, great work. Very excited about it. I was wondering what's the overhead that you have observed for
Yes.
running?
Thank
Thank you.
Yes, no, that's a great question. I don't have the numbers with me handy here. I don't know that we've actually shared numbers externally, but I think if it's interesting, we certainly could. We've definitely made improvements between the first version of our paravisor and this OpenHCL paravisor in terms of performance. I know this is not the best answer to your question, but I would claim that the performance overhead is smaller than you would expect, partly because of us using async Rust. But I know that's not a really clear answer because it's not numbers. I think numbers would be interesting, and certainly also comparing this to fully inline guests would be interesting. But yeah, I don't know that there's numbers out there today, and I don't know what numbers we could share, but it's something I can look into it and follow up on.
Thank you. Yeah, we're very interested in this. Yes, would love to follow up with you. Thank you.
Thank you for the question.
Okay, and I think
for follow-ups.
And I think we're down to the last minute or so here. So I think we'll wrap things up here. It sounds like everybody's going to be excited to see this code once it becomes properly open sourced, and you're certainly welcome and encouraged to come back when that is, and we can have maybe a deeper dive or talk about the governance of that code.
That sounds awesome. Thank you, Dan.